Chucha de tu madre. Ok. Continuamos hoy. Día. Hoy. Call. What the fuck is this? What? What is this? Let me see. I wrote down something in my notebook, but I don't even know what. Oh! Get that out. It was like this, bro. What a genius. Current Arity. And I said, oh, goddamn. Who's calling? What is Arity? Right? But no, niggas just calling Arity. My niggers. My niggers, my niggers, my niggers. Okay, the Brady, you nailed it. This is the last problem we did yesterday. It is here. Yep. So, yes, you're fucking right. The map perfectly checks out. You successfully. Humps. Perfectly equal train green. Okay. What do you mean? What do you mean, bro? Oh, yeah, I did it -2, right? I could have done just what? Raw 1 with the multiply version. What? I don't have to do that? Oh, really? Oh, I didn't know that. Okay. Well, but it still works, right? The rule of raw operation, when you see raw to clear our numbers below it, using raw pivot, you know the chain, the pivot raw. The operation is strictly. Oh, I didn't know that. I don't have to change the pivot raw. But it still works, right? But okay. But alright. But alright. But alright. When you're using raw to clear out numbers below it, using raw 1 is your pivot. You're gonna change the pivot raw. The raw operation is strictly R2. Okay. Yeah, I see. Five. Oof, claro, weón. You take the pivot raw every single time if you're going to drag massive loaded negative numbers in the entire system. It will increase the rows of making a stupid arithmetic error, like dropping negative sign. Yeah. Mechanics aside, you did the heavy lifting to a system where the inputs were unknown. Tore it apart mathematically and forced it to rebuild the secret to execute exact logic. I don't know if I did that, but alright. You say so, bro. You say fucking so. Oh, I gotta do fuck you. Okay. Bueno. Pingola. Vamos a... Wow, Machine Learning Fundamentals y toda esa weá, hermano. Qué piola. Pero bueno, vamos a... Ok, vamos a encontrar el libro. El librochis. El libroncio. Y ya, poco leamos. Vamos a hacer el librito. ¿No? Ah, lo tenía acá. No, déjame abrirlo. Yeah, right here. PDF, right? There you fucking go. Where's this one? Ah, ya. Ok, claro que wea. Bueno. Ahora sí vamos a hacer preguntas porque igual esto no entiendo, Igual esto no lo entiendo muy bien. Raw 3, okay, let's try that plane. Two, three, one. Ok, primero no entiendo por qué tenemos 4 vectors. Okay. So let's just start with the textbook. With the textbook. With my textbook related questions. Two is not equal to 1 plus 3, okay. Por ejemplo, for example, what the fuck is n here? What the fuck is n? Right, I don't know what is that. What the fuck is that? Fuck is n here? Okay, I think dot product, or it's just like or is just like a dot, and in the plane, in the I don't know, in the what, in the plane, right? No, not the plane. Oh shit, it's not in the plane because in the fuck you, in the diagram, in the combination, in the matrix. I don't know. What's the word in the what is even the word? What's even the word? Plane, diagram, 3D. I don't know. Okay. Yeah, why we have 4? Oh my god, now we have 5. They include. Yeah, but this is just like a line or a vector or a string or a string. Okay, yeah. First, explain me this. Explain this. Explain this shit, and then I will give it to you. Questions about this. Linear combination is this linear combination. Yeah, I'm getting kind of lost in this path right here. I wanna also watch the lecture, you know, which is this fucking one. But I'm not ready yet. I don't think I'm ready yet. These are the exercises. We're just in this fucking chapter, right? Portion of fig 2.2 from the textbook. Oh look, we also have to do 2.5, 2.1, and then just we can, I believe, watch the lectures, the presentation. Wait, what is it? What is the difference between this and the? It's the same, right? Nope. Oh yeah, that's that motherfucker. This lecture video. Nope. Okay, yeah, it's not that hard. Transcript, yeah, it's not that hard. It's pretty well described. So yeah, let me just ask this, and what else? What else? Perpendicular. 90 degrees angle. We're testing the products. Yeah, I'm not sure about this. Okay, V and W are the vectors, right? C and D are the constants. but alright. Yeah, sometimes people really work because I did not ask that, bro. How the fuck you, man? Oh no. Okay, my bad. Yeah, I said that. Yeah. Build good habits now. Oh, so let's start from that is not and it is a U. What? I don't see no fucking U. What do you mean? Oh, no, yeah, what do you mean? That's a different image, bro. Fuck you. Yeah, you're looking at the whole fucking different image. This one, you're looking at this or something like that. Come al pincho esto, güey. Span. Okay, you know what? I'll just make questions and questions. Esta huevada, yo quería ver esto todavía. Alright, so let me just ask this motherfucker. Span. Yeah. Linear algebra. En Hindi, en Tamil. Es increíble, weón. Yo. Pero es que ya lo vi, weón. Subspaces and span. Insane how to think span of any vectors. I mean, there are plenty of videos, right? Let me see this guy. Yeah, because I have to join my learning with some other sources, you know. Yeah, your skin's so pink right now.
Professor Dave here. Let's talk subspaces.
It looks sad.
He knows a lot about all kinds of stuff. Professor Dave explains.
Wait, I remember the song was like, he knows about the science stuff. About the science stuff, but now he's saying about all kinds of stuff, right?
Talk subspaces.
He knows a lot about all kinds of stuff.
About all kinds of stuff.
Dave explains.
Shut the fuck up, okay?
Once we understand what makes up a vector space, it is fairly easy to understand the concept of subspaces as well. To put it simply, a subspace is a smaller set within a vector space that is itself a vector space. Let's look.
Oh, so this is also a vector space. But this is a dot or a vector. What is
some
that?
Examples to clarify.
Please.
Let's say that V is a vector space. Now we can highlight this smaller section of V and call it S. Every element.
So one section of being called S. Every element of S is also an element of B. Yeah, right. Okay.
Of S.
So this is like discrete mathematics or not? Hold on. I'm cold. I'm cold over here.
Was already also in our vector space V, so we know they all obey the properties we discussed in the previous tutorial. This means that the only requirement we need to check in order to determine whether S is a vector space is that it satisfies the properties of closure. If S is closed, it will also be a vector space, and because it is completely contained in the larger vector space V, we will then call it a subspace of.
Let's color C, then CA. What? Okay, this second part I don't get it. Uh, oh, my bad. I thought that was also a scalar. No, it's just another subspace, right?
V.
No, 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 no. No, 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 no. S is the subspace.
Means that
A and B, what the fuck are those?
of S was already also in our vector space V, so we know they all obey the properties we discussed in the previous tutorial. This means that the only requirement we need to check in order to determine whether S is a vector space is that it satisfies the properties of closure. If S is closed, it will also be a vector space, and because it is completely we need so in the previous tutorial. This means that the only requirement we need to check in order to determine whether S is a vector space is that it satisfies the properties of closure. If S is closed, it will also be a vector space. And because it is completely contained in the larger vector space V, we will then call it a subspace of V.
Yeah, for sure.
We saw last
Yo, but what the fuck happened with A and that shit, man?
time
B.
that
Vector A
R3,
and
or
B.
the set of all real vectors of length 3, was a vector.
You know what? Shut your bitch ass up. You know what? Hold on, bro. So, S is a vector, right? It's a vector. But what about A and B? And those hats, both of those hats are both. Subspace S? That's a good question. I came here, you just told me some more shit. But alright. But I don't get it. What the fuck? The book is like telling me something they haven't even explained before. That's so weird, right? So crazy for me.
Subspace of V. We saw last time that R3, or the set of all real vectors of length 3, was a vector.
Okay, yeah, he's telling me. So this is, but isn't it weird? So we have a vector inside another vector. Sort of unreal vectors with 3 components.
Vector space. So now let's look at a specific choice of vectors contained within R3 and see if it makes up its own vector space, thus qualifying as a subspace of R3. For this example, we will choose a set S made of vectors that have the form x, 0, negative x. By limiting the form of the vector like this,
Necessarily in R3. Yeah, sure.
we have chosen a smaller set of R3, while knowing that our chosen set of vectors still follows the rules of the larger set. What we must check now is if our
How? Because they don't share the same components. Or
smaller
what?
set is closed by checking the 2 properties of closure.
Oopsie.
First, let's multiply a
Better. Hold on. God damn. Given x belongs as and scalar c, then x belongs as. Okay. Shouldn't this be between parentheses though?
vector x by
Inside parentheses or within
a
parentheses?
scalar c. Distributing the scalar c, we end up with a vector cx0 negative cx.
Yeah.
Notice that this still has the same form that we want for our set, with
What the fuck?
some value on the first row, 0 for the middle row, and the negative version of the first value in the third row. This vector is
Oh. Say that again.
form that we want for our set, with some value on the first row, 0 for the middle row, and the negative version of the first value in the third row. This vector is therefore still in our set S.
Still S. Wow, interesting. Wow.
Next, let's take two vectors, x and y, both from the set S, and add them together. Provided
Add them together. 0, 0. I don't think they are. Maybe they are.
that we factor the negative sign out of this sum, we will see that the third entry is simply the negative version of
Yeah.
the first.
So it
and
is.
once again, we find a result in the same form as we started. This means that the sum is also
out.
contained in our set S. We have verified that S is closed, making it a vector
Backman.
space. And because it was contained within the larger vector space V, this makes S a subspace of V. S is closed, making it a vector space. S. We have verified that S is closed, making it a vector space. And because it was contained within the larger vector space V, this makes S a subspace of V. Before going further, it's important to introduce a few more concepts.
Yeah.
Once again, let's say we have a vector space V and a number of elements of V, which we can call V1, V2, all the way to Vn. Any sum of these elements multiplied by some scalars, which we can represent as A1 V1 plus A2 V2,
The scalar is A, right?
and so on,
Yeah.
up to AN Vn, is called a linear
Linear combination, but the whole thing is a linear combination.
combination. The set of all possible linear combinations of these elements is
Okay, so this is a linear combination, but the whole shit is the span.
called their span. As an example, let's take three vectors from R3.
We can do a matrix here, right? And then just put it a constant outside.
Those being 2, 1, -1, 0, 2, 2, and -1, -1, -1.
Negative one.
The span of these
Hold on. But why you have these fucking constants? A and B and C.
three vectors will be given by the linear combination AV1 plus BV2 plus CV3, where A, B, and C are all scalars. Let's plug in our vectors and distribute the scalars, and then do vector addition.
Interesting. So I want to ask, how is that the same as this? Hold on.
And example, let's 0 of these 3 vectors. Let's plug in
Yeah. One D line. Yeah, I got that. So what? What the fuck are you explaining to me, bro? Oh, that's spam. Really? Oh, describe that plane. Hmm. Okay, figure 1.3. Okay. Oh, so these are just like examples. It doesn't matter, right? I believe. Right. I don't know, man. Okay, hold on. What do you mean by this? Oh, the fuck, bro. Yeah. It's raining and windy. Outside, bro. Yeah, it's windy as fuck. Man. Yeah, I'll have to leave though. Oh my god. Yeah. Let me check something. Let me see some. Okay, at 4 p.m. Okay, should be good. Should be good. Yeah. I don't know what the fuck is N. I still don't know what the fuck is N. Okay, this is a lot. This is a fucking lot. Please don't get overwhelmed. Oh my god. Because I am getting overwhelmed. Please don't you. You don't. What? Yeah, okay. We must introduce that third vector. You was just line on the same planets. Yeah, it would be redundant singular. Yeah. Oh, that's a singular. And you would still travel the 3D plane because it's okay. Okay, I get that. Perpendicular vectors have zero dot products. No, I'm gonna have to ask that. Is a zero dot product. Oh my god. I guess. The concepts are simple, but the alphabet soup makes it look like ancient Greek. What the fuck you mean with you, bro? There's not a single you. Okay, I'm giving you a lot of input. Fuck you, man. Let's go. Yeah. I don't know about that. un tarado, weón. Es un tarado. Me está explicando cualquier huevada. No, imbécil. No, 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 no. Ok, parece que aquí no vas a saber explicarme una mierda. No vas a ver, weón. No vas a ver. Ah, la puta madre. I'm gonna have to ask him like question by question, bro. Just one by one. Question by question. 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 By question. Bucket love for vectors. Makes sense. What the fuck do you mean matrix A? There's no A at all here, man. Right. Wait, really? Oh, the number of rows has to do with the dimension of the room, right? Yeah, but that's not what I asked, bro. I'm not even gonna answer. Just want you to. Oof. Yeah, 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 yeah. It's getting crazy. Oh my god. Why have two solutions? Oh, no, never mind, never mind, never mind. There's a different. Oh, my belly, my stomach. Oh, so you want me to say if these are either lines, planes? I mean, fuck you. I think this. Huh. Okay, there's a vector of 3. I think all of them should be three dimensions, right? I mean, this definitely is. Fuck you, man. Okay. Okay, hold on. My nigga, clearly says that if F is closed, then it is a vector space. So what the fuck are you talking about? Okay, whatever, man. Infinite floor. How the fuck is gonna be infinite, man? What? Yeah. But it's not infinite then. I mean, it's considered infinite because there are many options, I guess, right? Oh my god, no, you're so wrong. You're so stupidly wrong. Oh, fuck. This nigga, man. Fuck you, man. What hat? Oh, stupid. Oh my god. Oh, fuck. What image, bro? Okay, this is true. Measures how much two vectors agree with each other.
Has the
Okay, hold on.
AV1 plus BV2 plus CV3, where A, B, and C are all scalars.
Now they are scalars, but before they weren't. Were they?
Vector like this. For this case of V that contains that set of elements, minus C. The B and C are all scalars.
Okay.
Let's plug in our vectors and distribute the scalars, and then do vector addition to see that the span of these three vectors has the form 2a minus c, a plus 2b minus c, negative a plus 2b minus c. It's worth noting that the span of any number of elements of a vector space V is also
What the fuck?
a subspace of V. In fact, it is the smallest subspace of V that contains that set of elements, as it is the intersection of all subspaces that contain them. Span will end up playing a significant role when it comes to completely describing vector spaces. But for now, let's check comprehension.
Okay. Wow, this is fucking, yeah, this is fucking crazy, man. The zero matrix of the form AB, negative B, C is a subspace. Why 2 times 2, man? Or 2 by 2? Find their span. What the fuck? Oh my god. Okay, hold on. I think we're just gonna add them, right? Oh. Oh my god, okay. So I think this should be just 5a. What the fuck? And 0 minus b minus c. Is that true? I don't know. I don't know.
it is as vector spaces.
So this is their span, right? I guess. Just what it says. Let me see, man. I fucking good, bro. Come on, bro. True. What do you mean true? True what? Okay, I did. Oh. Yeah, it's. Wait, what the fuck? ¿Y por qué no hay una C, weón? No entiendo, hermano. ¿Qué carajo me estás hablando? A minus B? ¿Y este C, weón? No entiendo, causa. Will you explain me or you're just gonna... Oh, yeah. You're gonna explain me shit. No entiendo, causa. No entiendo. How and why and what the fuck? What the fuck? Oh my god, oh my god, my god, my god, my god, my god, my gosh, my goodness, my goodness, my goodness. The product. Vectors. The product. Oh, this thing is gonna teach me that. Alright. It's physics, two vectors, okay.
What you'll first do is we will resolve this vector into its horizontal and vertical components.
Vertical
so
component.
f cos
Equals work done. Force displacement, whatever.
theta becomes the horizontal component and f sine theta becomes the
Theta. Lo hice muy gracioso, ¿verdad?
vertical component. Now we can say the work done is equal to the force acting in the horizontal direction, that is f cos theta, into the displacement, which is d.
Carajo, qué puta madre, weón. Okay. Huh. FHD displacement. How the fuck is that dot product?
And you can also see that no work is done in the vertical direction.
FH, this FH. But both are fucking not perpendicular, both are same.
Because the displacement is 0 in the vertical direction.
0 in the vertical direction, yeah.
Now we can rewrite this expression as f times d cos theta, which in
Cos
turn
theta.
can be written as f dot d,
F dot B. What the fuck?
or the dot product.
Oh, yeah. Cosine theta. Man, I'm kind of forgetting a bit of trigonometry. Okay, we know sine is vertical and cosine is horizontal. Yeah, I need to
Of
do math.
F
I need to do fucking
with
math,
d
man.
is the work done.
Not only math, but yeah.
What you'll first do
Okay. Funny shit, man. Vectors, what is that product? Yeah, please explain.
Hi there.
man.
Today we're covering what
But you know what? This motherfucker is gonna it's actually gonna explain me in the fucking lecture. So I hope I really fucking understand. You know what I mean? You gotta fucking understand, bro. Why? Oh my goshness. Watched. What do you mean watch? I didn't watch any of this. Shorts. Yeah.
Hi there. Today we're covering what is dot product. Dot product can be calculated using either the
What the fuck?
formula shown here. But what are we calculating? Well, dot product is calculated by multiplying the magnitude of one
Vector by the magnitude of the second vector's projection on the first vector. Oh, just a projection.
vector by the magnitude of a second vector's projection on the first vector. So what does this actually mean?
I don't know.
Well, let's look at the example here. How do we draw the vector projection of A on B? The first thing we need to do is draw a line perpendicular from vector B to the head of vector A.
Okay,
Now,
good.
Using this right A,
Could put on a vector A parallel to vector B, component of B.
Angle, we can break our vector A into two components, one parallel to vector B and one perpendicular to vector B. We can ignore the perpendicular component for now, as the projection of vector A on B is just the parallel component here. Now to calculate the dot product, we need to multiply the magnitude of this projection by the magnitude of B. So how do we solve for the magnitude of our projection? Well, this projection creates a right angle triangle, and we can use SOHCAHTOA to solve for the magnitude of this projection, which is shown here. By multiplying the magnitude of the projection by the magnitude of vector B, we get the formula for dot product. We can get the same expression by instead using the projection of B on A and multiplying this by the magnitude of A.
My nigga, my nigga. My nigga, my nigga. Okay, so I think this is the fucking dot product. No.
Angle triangle.
Yeah, cosine goa. SOHCAHTOA. SOHCAHTOA. SOHCAHTOA.
And we can use SOHCAHTOA to solve for the magnitude of this projection, which is shown here.
Magnitude. Yeah, right? Yeah. Wait. Oh, right, sure. So this is the cosine of is it adjacent? No, adjacent hypotenuse. This is cosine. This is fucking opposite. Oh, what the fuck? What are you trying to do, man? Oh, my nigga, what the fuck? Hold on. Why? Oh, yeah. I guess. What the fuck? Oh my god, what the fuck? But I thought sine was the vertical one. No, it's fuck you, man. Explain this
So
shit
how do we
again.
solve for the magnitude of our projection? Well, this projection creates a right angle triangle, and we can use SOHCAHTOA to solve for the magnitude.
For the magnitude? What do you mean? Oh, this thing is censoring everyone, bro. Basically, this is how we multiply the vectors. In a sense, we are just multiplying the magnitudes together, but the cos theta is used to align the vector itself in the same direction. Oh my god.
We can break our vector A into two components, one parallel to vector B and one perpendicular to vector B. We can ignore the perpendicular component for now, as the projection of vector A on B is just the parallel component.
Just a parallel component of A. No, yeah, of. What?
Here. Now, the perpendicular component for now, as the projection of vector A on B is just the parallel component here.
Parallel component here. Okay, whatever.
Now, to calculate the dot product, we need to multiply the magnitude of this projection by the magnitude of B. So how
Check this projection. When you say projection, you mean this? Yeah, sure. By the magnitude B.
do we solve for the magnitude of our projection? Well, this projection
Oh, yeah. Hypotenuse is just vector A. Oh. Yeah, because... Wait! Oh my... Fuck you! This is projection A what? A parallel to B.
Example here.
Oh! Qué hija de perra. Ah, qué rico pedo también. Qué cae de risa. Bueno, because just it has to be the same magnitude. Oh,
how do we draw the vector?
Thank God, thank God. Un conceptito más para la bolsa, loco. Un conceptito más para la maleta, papi, tú sabes. Un conceptito después de una orilla. Pero yo creo que mientras más I think the more comes as I overcome or I collect as the times goes. Like the more foundations or basic concepts I'll get over time, just gonna be better on the long run, right? Yeah. But hold on, you haven't even finished this shit, so hold the fucking up. Yeah, hold on. You cannot take your break. Got like 5 minutes left. 5 minutes left. So harder fucking on. And we only passed one more problem. Not even a page in this motherfucker. We only passed. We didn't even pass 1.9, 1.18. I just got like bored of it, kind of. So, fuck you, man. Okay, let's
vector
finish
projection
this.
of A on B. The first thing we need to do is draw a line perpendicular from vector B to the head of vector A. Now, using this right angle, we can break our vector A into two components, one parallel to vector B and one perpendicular to vector B. We can ignore the
Fuck yeah.
perpendicular component for now, as the projection of vector A on B is just the parallel component here. Now, to calculate the dot product, we need to multiply the magnitude of this projection by the magnitude of B. So how do we solve for the magnitude of our projection?
Magnitude of B of the remaining magnitude. Fuck you. Magnitude of B.
Well, this projection creates a right angle triangle, and we can use SOHCAHTOA to solve for the magnitude of this
Right angle triangle.
projection, which is
yeah.
shown here.
Yeah.
By multiplying the magnitude of the projection by the magnitude of vector B, we get the
Hold the fucking on, bro. Hold the fucking on. Why would I? The magnitude of one vector. Oh, got it. Yeah, but the magnitude, the horizontal magnitude, I guess, the horizontal magnitude.
formula for dot product. We can get the same expression by instead using the projection of B on A and multiplying this by the
magnitude
magnitude of A.
Magnitude A. Interesting. Now, what the fuck is splitting that like so fucking different, bro? Maybe because I needed some graphics. I needed visual explanation, I guess. The ultimate ghosting. This was pretty good. Agree with each other. If the product is positive, they're pointing in the same direction. If the product is negative, they're pointing away from each other. They're perpendicular, they have absolutely zero overlap. They're orthogonal. Oh my god, now what the fuck is orthogonal, nigga? I don't know. Orthogonal matrix, decomposition. There's a lot of stuff about orthogonality. Orthogonal matrices. Oh my shit, bro. Explain. Holy fuck. What is projection? Oh yeah, I think I know what is projection.
A matrix Q is orthogonal.
Okay, hold on. The vector n. It then shows that if you take the dot product of n and any vector in your forest results are 0. When that happened, bro? Where the fuck that happened? In my note, in my textbook. That shit never happened, bro. That shit never fucking. Oh, yeah, it happened right here. That's where you go to the plane. By testing the products. Okay, probably gonna just have the products. Interesting. Why does this matter? Normal vector. If the dot product is 0, it means the vector n is standing perfectly straight up. 90 degrees away from your floor as the engineering and to it. Normal vector. another model was used for the what the fuck? Oh my god, this nigga's right. Holy shit, okay. That's crazy. So yeah, there are a lot of concepts in this shit. I never seen this. So yeah, that's cool. That's cool. That's cool. I fucking think no. We're still gonna just read through the fucking textbook, through the textbook. There's two problems. I think the problem set is kind of easier. The we have done so far. What is this? This 1.2. This is a little bit of reading, just reading. It can be easy. How fucking long is 1.2? MATLAB. And then we have some examples. And fucking another fucking problem set. Yeah. Fun shit. I'll put 1B. Nice. Does it click? Nah, it doesn't click, man. Not yet. A and B are just coordinates on the floor. As it divided itself and steer the product. Okay.
If Q
Let me just watch this video
transpose
out of
Q
fucking curiosity,
equals the identity matrix. That's the
matrix.
definition. To visualize this, let's consider two unit vectors that are perpendicular to each other. Say Q1 pointing to the right and Q2 pointing up.
In Kyoto. In Kyoto.
Consider two unit vectors that are perpendicular to each other. Say Q1 pointing to the right and Q2 pointing up. These satisfy our conditions. Each has length 1, so the norm of Q1 equals the norm of Q2 with
The norm. Is that what my guy just told me about norm or the normal?
our conditions. Each has length 1, so the norm of Q1
Oh my nigga, the normal. He said normal, right? Or the norm of.
equals the norm of Q2
Wait, no, he said norm. Oh god, orthogonal matrices. The norm is the same as the normal. Bitch. I gotta eat, bro. I gotta fuck. Yeah, I did 1 hour, but hold on.
which equals 1. And they are perpendicular, so their dot product Q1 dot Q2
Zero. Come on. Nigga.
equals 0. Now, here is something beautiful. If we rotate both of these vectors by the same angle,
90 degrees.
they remain orthonormal.
Orthonormal.
The rotation preserves their unit length and their perpendicularity. And the matrix that performs this rotation with entries cosine theta and minus sine theta in the first row with entries cosine sine theta and minus sine theta in the first row and sine theta and cosine theta in the second row, that's an orthogonal matrix. And we can verify that Q transpose Q does indeed equal the identity. Thus, any rotation matrix is orthogonal. And in fact, rotations are the most intuitive examples of orthogonal transformations. A matrix Q is orthogonal if Q transpose Q
I didn't get shit.
equals the identity matrix. That's the definition. To visualize this, let's consider two unit vectors that are perpendicular to each other. Say q1 pointing to the right and q2 pointing up. These satisfy our conditions. Each has length 1, so the norm of q1 equals the norm of q2, which equals 1. And they are perpendicular, so their dot product q1 dot q2 equals 0. Now, here is something beautiful. If we rotate both of these vectors
on.
by
But I thought that dot product was the multiplication of q1, or I mean, of the two vectors. And if we multiply them, we should get 1 at least, right? I mean, not even 1. I mean, let's say this is 1, this is 1. How the fuck we got 0? You know what I mean?
the same angle, they remain orthonormal. The rotation
I mean, I think it should be like a square if they have at least the same length, the same magnitude. So this is 3, 3. It's like it's just a square of 3. Right?
preserves their
Should
unit
be in that sense.
length and their perpendicularity. And the matrix that performs this rotation with entries cosine theta and minus sine theta in the first row and sine theta and cosine theta in the second row, that's an orthogonal
So that was the same.
matrix. And we can verify that Q transpose Q does indeed equal the identity. Thus, any
Transpose, yeah, transpose is just when you transpose it.
rotation matrix is orthogonal. And
I think transpose is when you put this 2 here and this 2 here. Kind of, yeah.
in fact, rotations are the most intuitive
Yeah, it's kind of the same, just different signs.
examples of orthogonal transformations. A mat
Say that again.
and in fact, rotations are the most intuitive examples of orthogonal transformations. A matrix
Interesting. Fuck you, nigga. Ok, hasta aquí el episodio de hoy. ¿Qué hemos aprendido? Uf, como mierda, como mierda. Bueno, dot product y ya, ¿no? Y ya, huevón. Y un poquito de N. ¿Qué he aprendido, huevón? Hablando en serio, ¿qué carajo he aprendido? Oh, span. Span. Hemos aprendido el span. ¿Qué es el span? Cuando todas las linear combinations se juntan. ¿Es that what span is? I don't know. O sea, cuando tenemos la same scalar, ni siquiera la same scalar, bro. Bueno, cuando tenemos varios linear combinations. Eso es el span. Okay. Is the span where we have the same scalar in a vector or at least okay. At least many linear combinations. And if dot product is a multiplication of two perpendicular vectors, how is that 0 if they have the same magnitude? Shouldn't they be the fucking square? Actually, okay. Bueno, a la mierda. Son muchas preguntillas. Gotta get out of here. Gracias por ver.